All right. Thank you for the lovely introduction. Good afternoon, everybody. Thank you for coming to this talk. It's great to see so many people excited about reactive programming. As was said before, my name is Miro Cupak. I'm with a Canadian company called DNA Stack, where we've built a cloud platform for genomics. And if that's something that you're interested in, please come find me after the talk. But this talk is about Java and reactive programming. So let me just start by saying that reactive programming is pretty great. But one small issue that I have with it is that it became a buzzword, right? It's often described as this standalone, completely new paradigm, and I don't think that's too grandiose of a term in this context. Whereas in reality, it's actually not new. As a methodology, it's a collection of principles that individually have been around for a very long time. And as a technology, it's also built on top of other technologies that we've had for many years. But I think that this larger context is an aspect of reactive programming that is often overlooked. Yet it's very useful to help us understand what reactive is all about. So this is going to be a slightly different kind of reactive talk in that I'm not going to talk about a particular reactive library or reactive framework. Instead, I'm going to focus on this larger context. I'm going to talk about the building blocks for reactive programming that we have available directly in the JDK right now. So in the next 40 minutes or so, I'm going to take you through what I call the 8 levels of reactive, which correspond to the features in the JDK in the order they were added to Java, and also, not coincidentally, in the order that makes your system more and more advanced. But before we get to that, I should probably start by defining what reactive actually is about. And reactive is basically about creating systems that respond to events as they happen. So it's basically a cool name for a collection of principles that allow us to create systems that are responsive. And to be responsive, we need to be elastic, we need to be able to handle varying loads, and we need to be resilient to failure. That doesn't mean that we can't throw errors. We can throw errors, but we need to handle them, and we need to be able to contain them reasonably well. And it turns out that a really good approach towards elastic and resilient is through having a system that's message-driven, particularly when it comes to asynchronous messaging. So these 4 properties, responsive, resilient, elastic, and message-driven, that's really what reactive is all about. Now, before we go any further, there's one thing you should know about me. I'm bad at making slides. So I've prepared exactly 4 slides for you today. This is one of them. And this is another one of them. And as this slide suggests, the rest of this talk is going to be a live demo. I like learning through examples, so I'm going to write quite a few of them throughout this talk. And I'm going to write them in JShell, which is Java's implementation of a REPL that we've had since version 9. If you haven't seen JShell before, don't worry about it too much. It's very easy to figure out. So let me just switch to it here. If it's not readable or anything like that, please do complain. We'll sort this out. But hopefully the font is big enough for this. Anyway, so on our journey through the history of Java and levels of reactive, let's start really far in the past. Okay? Let's start with the very first version of Java, Java 1. So since the very beginning, we had some constructs for parallelism, right? And reactive programming is basically a particular take on parallelism. So in JDK 1, we had runnable, and we had its implementation, thread. So I could do something like this. I could create a new thread and give it a runnable here. Let's say just a quick lambda. And let's just print out hello Thessaloniki. And let's call this T. Then we can, of course, start the thread. And it's going to print out hello Thessaloniki. And that's very nice. That was a big deal at the time, right? Because now we had this abstraction in the JDK, and we no longer had to write native code to manage threads. But it was pretty much all we could do with threads at the time. More specifically, we had no sophisticated mechanism for coordinating threads and things like that. So I'm going to call this level 0 reactive. We're parallelized, so we're taking the first necessary step towards reactive. But obviously, we're very far from a reactive system. And you shouldn't try to implement a reactive system on top of threads directly. It's a very low-level construct. They're very heavyweight. And there's just so much other stuff that you would have to implement yourself. But it was a good first step. Things got a bit more real with Java 5, though. Java 5 introduced 3 interesting interfaces. There was executor service, there was a callable, and there was a future. Executor service is basically a framework for execution of tasks, so runnables. In practice, we're essentially talking thread pools. Callable is kind of like unrunnable in that it's a representation of a task, but this task can return a value and can throw an exception. And future is a result of an asynchronous computation. So this is how these three things work together. I can create a new executor service. Let's just create a single threaded executor. That's all I need for this very simple demo. And let's call this E. And then I can submit a task, which is a callable. So let's do a quick lambda, and let's just say, hello, Thessaloniki. And you will see this string appear many times throughout this talk. It's our go-to string for the next hour. And let's call this F. So this, of course, returns immediately, and the future is not completed, as you can see here, because it's asynchronous. But of course, it completes very quickly. So if I take a look now, it's actually completed normally. And I can use the get method to extract the value in the future. And of course, it says, hello, Thessaloniki. So these three things actually give us quite a sophisticated asynchronous system. So I'm going to call this level 1 reactive, right? This is no longer a simple parallelism. We can do asynchronous now, and it's actually very, very powerful. But these futures here are still too low level of a construct, and they're hard to compose. Basically, what you see in practice when people are using futures, when they try to orchestrate a workflow where they have a task depending on outputs from other tasks, they do this sort of busy waiting where they iterate over their futures and they keep checking, is this done, is this done, is this done? And then when all the futures they need are done, they issue a new task. But they have to be blocking on the main thread to coordinate this. And being blocking is not very reactive. Being non-blocking is a very core part of being reactive, in fact. On top of that, the get call that we executed here is actually also a blocking call. So I can run things asynchronously, but then to coordinate or to actually access the result, I have to block. And that's just not good enough. From a reactive perspective, it's very important to avoid blocking threads. You want to optimize your CPU. And it's very important to avoid changing threads as well, because context switching is expensive, right? A new thread is likely to require different data, which the CPU needs to pull in, and you need to optimize your use of cache. So that's how far your system needs to go to be reactive. So this really was made easier with Java 7, which introduced the fork join framework, and more specifically, the fork join pool. Fork join pool is an implementation of executor service. In other words, it is a thread pool, but it's very suitable for asynchronous programming because it understands that certain tasks depend on other tasks, and it doesn't move things around between CPUs unless it's necessary. So basically, it provides better utilization of resources for asynchronous programming. The key assumption behind the fork join pool is that newly created tasks are more likely to have data in a closer cache, right? So essentially, maybe it's a good idea to execute these on the same CPU and offload some of the older tasks to a different CPU. And that's really how it works. So I have a bunch of threads. They keep working on tasks. Each thread has a local queue. I add new tasks to the queue. The thread keeps working on it. When it's done, it says, hey, I'm done. Do we have anything else in my queue? And it takes the next task. So when a task needs to schedule more work, it basically adds more tasks to the local queue. So here's the assumption, right? I'm not moving to another CPU unless I need to. So how do you scale this across threads? Well, each thread has its own queue, and they keep working on their tasks. And when they're done with everything in their queue, they perform something that's called work stealing. So they basically steal a task from the bottom of someone else's queue. So again, here's the assumption that if I'm taking something from the bottom of someone else's queue, it's probably OK to offload it somewhere else because it's like the least performance penalty. And it turns out that this just performs remarkably well for asynchronous programming. In fact, it performs so well that fork join pool is the basis of all the reactive components we're going to mention throughout this talk. So if I wanted to use the fork join pool directly, I can just utilize my example from before. I can create a new executor service by just tell it to use fork join pool, for example, just the common pool. And then I can still submit my task the same way and extract the value the same way. Of course, this is a very primitive way of using fork join pool, but it's good enough for us for these demonstration purposes. So with futures, we're asynchronous, right? With the fork join pool, we can do asynchronous really well. And having really great performance for asynchronous programming is at the very core of reactive. So let's call this level 2 reactive. And this is the good level to be at, but there's still quite a few building blocks that we'd have to build ourselves if we just wanted to create a reactive system on top of this. The main problems that we have at this stage are that futures are hard to compose, and you need to block on the main thread when you're trying to coordinate, right? But as it turns out, Java 8 helps us with this quite a lot, actually. Java 8 introduces completable future, which is basically a framework for primarily non-blocking asynchronous programming in Java. It's all built around this class called completable future, which, as the name suggests, is a future that can be explicitly completed. So you can set its value and its status. And we have APIs for creating dependencies in the futures. So when I say it's a future, I mean it literally implements the future interface. It also implements another interface, which is called completion stage, which is also something that was introduced in Java 8. And completion stage is basically a representation of a stage in a larger computation. So essentially, we use completable futures to model tasks in a more complex workflow that consists of many tasks. Primarily, we're looking at asynchronous workflows. So completable future addresses several problems we had with futures. It makes things easy to compose. We don't have to block anymore when we're coordinating things. And it automatically uses the fork join pool behind the scenes. So it's actually very effective. And that's really great. So how does it work? Well, the basic API is actually pretty simple. I can create a new completable future, let's say of type string. And let's call this, let's close this, and let's call this CF. And then I can complete it, which needs a value, in my case a string. So say this is done. And now I can use the get method that we already know for the future interface to access the value. So what happens if I don't complete it? Well, let me just reset here. I can call the get method directly, and you can see nothing happens, right? Remember, this is a blocking call from the future interface. So this is going to be blocking until somebody else completes the future for me. But I'm not going to wait around for that. So we can complete futures normally, but we can also complete them exceptionally. I can call the method complete exceptionally here, which takes a throwable. So I can just give it, let's say, new illegal state exception. And now, if I call the get method, it's actually going to fail with the exception that I gave it. So this is sort of the basic functionality. You can complete futures normally, and you can complete them exceptionally. Let's maybe try a bit of a more realistic example. I'm going to create futures in a different way, in a single pipeline, and I'm going to do everything asynchronously, which should point out the benefits for reactive. So let's start by creating a completable future like this through supply async, which, as the name of the method suggests, it's an asynchronous method, runs in a different thread, and it takes a supplier. So I'm going to just create a very simple supplier here. Let's say something like this. So I have this task, then I can chain other tasks onto it. Once this task is done, I can, for example, apply a function. Let's do this asynchronously as well. So I can say, OK, use this function that actually appends another string after my original string. And then I can keep going. I can call another method after this, maybe then accept, which requires a consumer. So I can just say print out the result. And you can see that it prints Untitled Thessaloniki. So this is sort of a very simple pipeline. I'm just creating the basic dependency. I'm creating a setup where one task runs after another task, right? But it shows a very, very crucial aspect of the completable future API. Basically, almost anything I do to completable futures also returns a completable future. So you have this sort of fluent functional API for modeling your workflows, which is actually very, very useful. So with completable futures, Java 8 gives you a pretty powerful framework. But as you start using it, you'll probably realize there are still a few things missing in it. Fortunately, Java 9 largely fixes that. Java 9 introduces, well, quite a few methods, actually. I would describe most of them as utility methods. There's some factory methods and methods to support subclassing of completable future, should you ever need that, but you probably won't. So these are not very exciting. But there are three methods that I'm really excited about. Java 9 basically introduces a new way of completing completable futures, and that's based on a timeout. So if I just reset here, I can now complete this future based on a timeout, which takes a value, in my case, a string. Let's say timed out, and then the actual timeout. So let's say 5 seconds. So now, if I call the get method, you can see that it's basically going to wait around for 5 seconds to see if anybody completes it. And if nobody does, it's going to be auto-completed with this default value that I gave it. So this is completing futures normally based on a timeout. I can also complete them exceptionally based on a timeout. That's the other method in Java 9. If I just reset here, I can call the or timeout method, which just takes the actual timeout. So let's say 5 seconds again. And now, if I call the get method, again, waits for 5 seconds, see if anybody completes it. If nobody does, it's going to be completed with a timeout exception. So these are the first two methods, right? Completing futures normally and exceptionally based on a timeout. The third method that I'm really excited about here is the method copy. And the method copy essentially creates a defensive copy of a completable future. And this might not sound like much, but it was actually the crucial missing piece for creating asynchronous APIs. When I say asynchronous APIs, I mean APIs that return completable futures, right? In this case, you basically want to provide sort of one-way synchronization. You want to return completable futures to the clients of your API, and you want them to be able to chain actions onto them and respond to changes. But you don't want them to be able to complete the future that you're using internally behind your API, right? In other words, you want them to read, you don't want them to write in a completable future way. And that's basically what this method allows you to do. So we can demonstrate this here. I'm just going to recreate my completable future, and I can create a copy. Let's call this copy. Now, if I complete the original, of course, the original is completed. Nothing sneaky happening here. But if I take a look at the copy is now completed as well. And in fact, if we try to extract the value from it, it's going to be the value that I completed the original with. So what happens if I do it the other way around? Well, let's try this. Let's reinitialize the original. Let's reinitialize the copy. And now I can complete the copy. And of course, copy is completed, right? But if I take a look at the original is not completed. So the clients can read, but they cannot write back, right? And this is just incredibly useful for building asynchronous APIs. So let's call this whole completable future system level 3 reactive, right? Completable futures get us very far. You could absolutely build a fully reactive system on top of this, and people have done that. They address the main issues that we had with basic futures. They make things easy to compose, and we don't have to block. And notice that we didn't see any threads anywhere, right? This is all hidden behind the scenes. It's abstracted from. So it might seem like a very low-level primitive, but it's actually not that low level. It's quite usable for reactive, in fact. So what are we missing then? Well, so far, we've been executing workflows on individual objects, right? Individual pieces of data. Wouldn't it be cool if we can handle live data, streams of data as it's coming in, right? And if you started implementing this on top of completable future, you would probably very quickly realize that there might be problems. For example, your producer might be producing data faster than your consumer can consume it. And that's something that you need to deal with, right? So what do? Well, you can drop the data, but that's not very good. You can block, but that's not very reactive. Or you can buffer it, but then eventually you will run out of the buffer. So you need to deal with that. Or you can implement some sort of an asynchronous communication model between the consumer and the producer, maybe some sort of a backpressure. And that brings us to reactive streams. Reactive streams is the de facto standard for asynchronous stream processing with non-blocking backpressure. The concept of backpressure really comes from the metaphor of a water pipe. If I'm at the end of a water pipe and I'm receiving water and there's too much water, what I can do is adjust the valve, adjust the tap, right? And that decreases the pressure on me, but it increases the pressure back to the source, right? Backpressure. And this backpressure concept is really integral to the reactive streams model because that allows our queues to be bounded. And having bounded things, it's very useful when you have finite resources. Java supports reactive streams since version 9 through the Flow API. Flow API consists of two classes. There's the Flow class, and there's the Submission Publisher class. The Flow class contains 4 nested interfaces, which correspond to the basic reactive streams concept. So there is a publisher interface who produces the data. There is a subscriber interface who receives the data from the publisher. There is a subscription, which is the link between the subscriber and the subscription. This is how we implement backpressure. And then there is a processor, which is both a subscriber and a publisher. So the purpose of this is essentially a transformation function somewhere along the way, right? Processors can sit between your publisher and your subscriber and do some sort of a modification on your flow. The other class, submission publisher, is just sort of a reference implementation of the publisher interface from the flow class. So let's implement a simple flow here. I'm going to create a publisher and a subscriber that receives messages one by one as they're coming in. So let's start with the subscriber. I will create a simple class here. Let's call this simple subscriber. And this is going to implement the subscriber interface. Let's say subscriber of string to keep this simple. And now I need to implement all the methods defined in the subscriber interface. So there are 4 methods like this. The first method is method onSubscribe. So public void onSubscribe, which takes a subscription. Let's call it sub. And this really is the first method that's called on the subscriber. It's called when you register the publisher with the subscriber. And it essentially kicks off all the communication. There is a typo. Thank you. Good catch. So this receives a subscription, which is what you use to control the flow of messages between the publisher and the subscriber. So essentially, the subscriber can say, "Oh, give me some more data," or I request that you don't send any more data. Another method here is method onNext. So public void onNext, which takes a message. In our case, that message is a string. So let's call this item. And onNext is basically called whenever a publisher publishes a message. So we're implementing all the callbacks on the subscriber, right? Then we have a method onError. So public void onError, which takes a throwable. Let's call it t. And this is the last method that's called on the subscriber. It's basically called when there's an error that we cannot recover from in the publisher or in the subscription. So nothing else is going to be called after this. And similarly, we have a method onComplete, public void onComplete, which does not take any arguments. And it's similar because it's the last method that's called on the subscriber. But in this case, of course, it signals a successful completion. So for example, the publisher was closed. So let's try to close all of this and see if I got the contracts right. And thanks to your colleague here, I did. So that's very useful. So let's try to actually implement these methods. So first, I'm going to need some sort of a subscription, right? That can be useful. So let's create a private subscription. And again, the same typo. Let's call this sub. And then in the first method that's called, which is the onSubscribe, I'm going to initialize this, right? This sub equals sub. And of course, what I can also do is actually request the first message. So I'm going to request one message here. Subscription actually has 2 methods. There's a request method, which is how you implement backpressure, and there's a cancel method. So in the request method, if you give it a positive number, it means that you're going to receive up to that number of onNext calls. Up to, because the publisher might be closed in the meantime. If you give it 0 or negative number, it results in the onError callback with an ILO argument exception. And if you give it max value, as in long max value, it means it's an unbounded subscriber. It's just going to keep receiving forever. So that's on onSubscribe. And onNext, I just need to handle my message. So I'm going to print this out. Let's say I'm going to acknowledge that there is a message received and my item here. And then I can request another message, just like this. In onError, I'm going to implement the best possible error handling. And in onComplete, I need to clean up. Of course, there's not a lot to clean up right now, so all I need to do here is actually print out that we're done here. So let's try to compile this, see if this works. And this is looking good, first try. So that's promising. So let's try to actually instantiate this subscriber. Let's call this sub. Looking good. OK. So we have a subscriber. Let's implement a simple publisher. And like I said, this is going to be easier because the JDK already provides an implementation for this. The submission publisher is actually meant as a base implementation for your own publisher, but it does everything we needed to do for the purpose of this simple demo, so I can just use it directly. So I'm going to create a new submission publisher of type string, of course, to be compatible. Let's call this pub. And the publisher has a bunch of methods, but the publisher interface only prescribes one, and that's the method subscribe, which is register the subscriber with the publisher. So let's just try and call that subscribe and give it a subscriber. No error messages or anything like that. That's good. This actually resulted in the onSubscribed callback on the subscriber. And if there was an error, it will result in the onError callback, where I implemented print stack trace. So the fact that we're not seeing anything here is actually a good thing. But we can try and check if we have any registered subscribers. We do have one. So let's try and actually submit a message here. And my favorite string, let's see. And we can see that the message was sent and the message was received by the subscriber, right? So I can try it a bunch of times. It's very reliable. And then, of course, when I'm done, I can close the publisher. And of course, the subscriber is going to clean up as well. And if I try to send more things now, of course, it's not going to work. The channel is closed. Right. So we have a very simple working publish-subscribe model here, which is actually very cool. And it's actually not that simple. It's actually quite sophisticated because we use this submission publisher here, and that submission publisher is actually quite smart. It uses the fork join pool to deliver messages to the subscribers. It uses completable future behind the scenes. And it has a bunch of other stuff like error handling and buffering and that sort of thing. So it's pretty good. Having said that, you should never implement a reactive system like this. What we have in Java is meant to be an SPI. It's something that developers of reactive streams libraries should implement. You shouldn't have to implement it yourself. But all the concepts that it uses map one-to-one to the concepts used in those reactive streams libraries. So just a note, it's useful to know this, because that's what's being used in real life. But do use the library. Don't try to do this yourself. That's a lot of corner cases that you would need to handle. So let's call this level 4 reactive, right? We're pretty close to a full working reactive model, but we don't have the implementation in the JDK yet. So where can we go from here? Well, all this is great for passing messages between threads in the context of a single JVM. But a true reactive system needs to be resilient. So you're probably looking at a system that has a couple of services at least, and they would typically communicate over HTTP. Which brings us to Java 11 and its HTTP2 client. Java 11 basically introduces a new client API that replaces the old HTTP URL connection. And it supports all the cool new things. It supports HTTP2, supports WebSocket with TLS, supports server push, proxies, cookies, you name it. So in order to demonstrate the functionality of the client, I'm going to need a server. And if there's anything that I've learned from doing live coding at conferences, it's that you cannot rely on the Wi-Fi there. So I'm going to implement a very simple server here. And I like this example. It uses really old APIs in Java, but many people don't realize that we actually have this functionality directly in the JDK. So I'm going to create the simplest possible server. It's going to have a single endpoint, and no matter what I send to this endpoint, it's going to respond with a fixed string, right? So let's try by defining the handler for this endpoint first. Let's call this handler, and this is going to take an HTTP exchange and do a quick lambda here. Actually, not so quick. It's going to be a multi-line lambda, but that's OK. Let's define the string that we want to return. I think you can guess what it's going to be. And let's set the response headers. So I'm always going to respond with 200. Everything is OK. And attach the length of my content. And then I will need to open an output stream, assign my response body here. And then I will use this output stream to write my string to the response. And it's an output stream, so I have to do this through get bytes, but that's OK. So let's try and close this, and let's double check this handler here. This is looking good. OK, let's create a server here. HTTP server create, and this needs a port. So let's give it, let's say, 8000, and don't need the backlog. Let's call this HS. And now I can create my endpoint. Let's say /hello, and attach my favorite handler here. So let's try starting the server, and hopefully the server is working now. Now to test this, I'm going to need a client, so let's build a simple HTTP2 client. The new HTTP2 API is built around 3 classes: HTTP client, HTTP request, and HTTP response, which should be pretty self-explanatory. So let's start with the client here. HTTP client, new HTTP client factory method. Let's call this HC. We can take a look at the version here, and you can see that it does support HTTP2, even though I'm not really taking advantage of this. Then we can create the request, which actually uses the builder pattern. So I'll just obtain an instance of the builder here, give it a URI to my local server, which is going to be something like HTTP localhost. I believe I used 8000 /hello. Make this a GET request and call the method build, and let's call this a request. And then I can use the client to send the request to the server. And by the way, this also needs something called body handler here, but I'm just going to tell it to treat everything as strings, and there is a built-in handler for this, thankfully. So let's just do that, and let's call this response. And now let's test everything. Let's see the status code, 200. This is looking promising. Let's try the body, hello Thessaloniki. Great. Working server and a client. Thank you. This, of course, is a synchronous call over HTTP, though, right? And synchronous is not very reactive. But the client is actually very flexible. If I wanted to make this asynchronous, all I need to change is the send to send async, which now, of course, is going to return a completable future. Let's call this response again. But everything else still works the same. I can extract the body, and it just works nicely. So now we can do asynchronous calls over HTTP, and we can do reactive streams and completable futures on each end. So it's a very, very nice reactive system. In fact, the HTTP2 client itself uses the reactive streams model underneath, and it uses completable futures. So everything kind of ties together. So let's call this level 5 reactive. Should you build your own reactive system using these constructs? Probably not. There's still a lot to build, but this is what we have in the JDK right now. So what should you do? What is reactive beyond level 5? Well, there are a couple of things that are still missing in the JDK when it comes to reactive streams that you would most likely need in a real-life scenario. We don't have any operators, even really basic ones like map or filter. We don't have mechanisms for restarting, dealing with cycles, modeling concurrency, plugging, different buffering strategies, monitoring, tracing. All these things are very hard to implement. But thankfully, there are libraries out there that do this for us. So I would say that level 6 reactive is using a proper reactive streams library. And there are a few good ones for Java. The most well-known ones are RxJava and Reactor, which are both very good choices, both very mature, tested in production, backed by very large companies. And they do a very good job when you're passing things between threads in the context of a single JVM. But at some point, probably, you might want to take this to the next level and have a fully distributed system, microservice-based system, in which case you might be better off trying some sort of a higher-level framework that builds on top of these libraries. So I would say that level 7 reactive is using something like Vertex, which is actually built on top of RxJava, or Spring 5, which is built on top of Reactor by default. Or maybe you just use reactive streams, but you connect your services through a distributed streaming platform, maybe something like Kafka. So you can see that there is a clear trend with reactive programming in Java, right? Over time, things are moving from the plate of reactive stream library developers to the JDK, and we can definitely expect this trend to continue. We're currently at level 5 reactive with the JDK, which means all the building blocks are already there, but it's still relatively low-level constructs that you shouldn't use or implement directly. So as an application developer, you should still use a library or maybe even a higher-level framework. And there are many things out there to choose from. They all come with their own baggage, so just be careful when you're choosing what kind of baggage you want to deal with. And that's it for me. If you have questions, I believe we have a little bit of time, but regardless, I'll be around, so just come by and say hi. If you want to come back to the code that we've produced here, I don't really have it in the slides, but what I can do and what I will do is export my JShell session and post it to Twitter. Here's my Twitter handle. And otherwise, thank you, and enjoy the rest of the conference.
OK, we've got time for some questions. Who wants? Hands aloft.
Hi, thanks for your talk. I wanted to ask if there is any thought in the JDK community to add stuff to the language like async await style asynchronous programming, like we have in Node.js or C#.
I'm not aware of anything like that. The next thing that I can think of that's being added into the JDK that's related to reactive programming, and I think it's coming in Java 12, is Project Loom and fibers, so basically lightweight threads, which is obviously going to make things a lot easier and better. But nothing really like that, to my knowledge.
Next time. Come on, you must have some questions after that. Tumbleweed. Sorry.
OK.
All right. OK. Right, before you leave, though, when are you going back to Toronto?
In a few days.
Yeah? Right. Well, you're going to have to take care of this.
OK.
This is an olive tree. Tell me, give me a show of hands, please. Those of you who are from Thessaloniki. Hands up. And those of you who are from out of town. Keep them up if you're from out of Greece. There's a few of you. There's a few of you. Right, OK. Well, you're going to take a piece of Thessaloniki with you. Treat it with care. Treat it with love. Remember what Christina said? You have to care about something else if you're going to survive burnout. So take a piece of Thessaloniki, and if you look after it, it will give you olives.
Thank you very much.
So thank you, everybody.